All right, what's going on, Townview? So today we're going to be talking about gas laws. We're going to be starting out right here at the very beginning with Boyle's law. So right at the top of your notes, we're going to write gases, and let's go ahead and move on. So first thing I want to go over is kinetic molecular theory. Those of you who are in my class, we did kinetic molecular theory last week. I'm pretty sure you don't know exactly what I'm talking about, but through that simulation that you guys worked on, you should have learned every single thing on this list. So I don't want you to write these things as you see them. I want you to reiterate them and write them in your own words. So let's go over them real quick. So the first rule of kinetic molecular theory is that gases consist of very large numbers of tiny spherical particles. Well, we already know that because we know everything is made of atoms. And it says here that they're far apart from one another compared to their size. So that's not really new information. It's just something you need to know. This is one of the rules of kinetic molecular theory. Now the second one, it says that gas particles are in constant rapid motion in random directions. This is very important. So the gas molecules, they're not all moving to the left. They're not all moving to the right. They're not moving together. They're all moving randomly in random directions. And I could pull up, I'll pull up the simulation in a minute to show you. Actually, I'll pull it up now. All right, so if we take a look at this simulation, you can see that the gas molecules are all moving in rapid motion in random directions. So that's what we mean by that. The next rule of KMT says that collisions between gas particles and between particles and the container walls are elastic collisions. This is very important to know. So there's two types of collisions. There's elastic collisions and there's inelastic collisions. So to explain elastic collisions, I'm going to explain inelastic collisions. So let's say you have we're playing billiards here, and this is a billiard ball. So that's the red one, and then over on this side, we're going to put in the black one. And then we're going to hit this one with 50 newtons of force. So 50 newtons of force hit this one, dead center. And then this one is going to hit this one, also dead center. And what's going to happen in an inelastic collision? In an inelastic collision, which are the collisions that you guys are most used to, the energy is going to be transferred from this one over to this one. There's going to be an energy transfer. Most likely, this ball is going to stop at this position. It's going to stop right here. And then this one is going to move forward with some of that force. We'll say 50 newtons, even though we know that a lot of it's going to be lost to friction. But we're just going to say that it's 50 newtons and there's a complete transfer of energy. And the red ball is going to stand still in this space right here. So that's an inelastic collision. Now, what's an elastic collision? An elastic collision is when something bounces onto something else. Let's pull up our simulation again. It's when something hits something else and then just moves away without losing any of its existing energy. Now, why is that important? So think about a basketball. So we have a basketball here, and we inflate it in the morning, and we get it up to, let's say, 30 psi. So we know that the gas molecules are constantly colliding with each other. They're constantly colliding with the wall. If the energy were to transfer when the gas molecules hit the wall, what's going to happen to the pressure of the basketball after, let's say, a couple of hours? So I'm going to pause right here. So the important thing to remember about elastic collisions is there's no energy transfer. All right, so the next one. There are no forces of attraction or repulsion between gas particles. You know what that means. It means they're not attracted to each other. There are no bonds between them, and they don't repel each other either. Now, the last one says the average kinetic energy of gas particles is dependent upon the temperature of the gas. This one is very important. We've been talking about this one all year. So average kinetic energy is just another word that we use for temperature. Now, why is that? If we look at this right here, you can see that they're not all moving at the same rate. So this one right here, let's find one that's not moving at all. As soon as you find one that's not moving, that one right there, watch, it's about to get hit, and then it's going to move. So are they all moving at the same rate? No, they're not. But how is it that we're able to determine how fast they're going? So that's what temperature is used for. So we use the temperature of the whole thing to give us the average kinetic energy of everything in the container. So I can't tell you the speed of any one particle, but I can tell you the average speed of all the particles together. So that's what we use temperature for. So let's come back over here. So what is average kinetic energy? Average kinetic energy is the average speed that all the molecules inside the container are moving. And we use average kinetic energy as so temperature is average kinetic energy. All right, so these are the rules of kinetic molecular theory. And what's most likely to happen on the test is you're going to see 5 options and you're going to have to choose the one that doesn't work. So as long as you know these, then you're going to be okay. And if you see something that doesn't make any sense, then you'll know how to answer that one. Now, if we come back over here, what I see very often is that they'll switch the word elastic with inelastic. So if this said inelastic, would it be true? No, it would not. So that's just what you need to know. Now, over on this next page, I got a quick check for you guys. For those of you here in class, I want you to use your phone or your computer, go into Classroom, and then open up the quick check. It's posted in there for you. I'm going to give you 3 minutes to answer these 3 questions. These are most likely what you're going to see on my test and also the ACP. You should be able to answer these with the notes you took down from the previous slide. All right, let's go ahead and move on. So here we have what's called the combined gas law. So the combined gas law has, it's got 4 laws in it, and it itself is a law. The reason I put it up here in the very beginning, I like to show you all the variables so that we can discuss all the variables in the equation. So first thing I want to go over is the 1. So what does 1 mean? 1 means initial. And what does initial mean? Initial means the start or the beginning. So if you walk into my room in the morning and it's 50 degrees, and then by 9 o'clock it's 70 degrees, the initial temperature would be 50, and the final temperature would be 70, or whatever it is that we decide is the final. So 1 means initial. You're going to hear me say initial a lot. Now the next one, 2. 2 means final. Final is going to be the end. So I'm going to be referring to these as initial and final from now till we're done with gas laws. But just know, that's what the 1 and the 2 mean. Now let's come back to these variables. So we got P, and these are all labeled. So P, of course, is going to be pressure. This is P1, which means initial pressure. V1, initial volume. P2, final pressure. V2, final volume. So that's all those are. Now N is going to be number of moles. So N, it says quantity, number of moles. And then T is going to be your temperature. And temperature, once we get to the temperature equations, we'll talk more about it. But temperature needs to always be put in as Kelvin. So we can't put in Celsius. We can't put in Fahrenheit. Temperature has to be Kelvin. And that's all that is. Now, another thing I like to do on this slide is show you all the formulas that are inside this formula. So let's say we have 20 moles. If we put 20 here, and I'd like the class to answer me in unison over here. If we have 20 moles in the beginning and we have 20 moles in the end, do we need to divide both sides by 20, yes or no? No. Why not? Because what is it? What's the word for it if it doesn't change? Constant. It's a constant. So anytime you have something that doesn't change, a constant, we can eliminate that part of the equation. So over here, that means that our number of moles is not changing, and we don't need it in the equation. Now, let's say our temperature was also 50 degrees on both sides. Would we need to keep T1 and T2? No, we could eliminate these from the equation. Now, what did this equation just become? So this just became Boyle's law. This is the law that we're going to be talking about today. But that's one part of the equation. Now, the next thing I want to show you, the next part of the equation, let's assume that our number of moles is constant and our pressure is constant. So this right here would become Charles' law. Charles' law is V1 over T1 is equal to V2 over T2. Now, if our volume was constant and our moles was constant, now this just became Guy-Lussac's law. So P1 over T1 is equal to P2 over T2. The valuable thing here, what I'm trying to show you, the important part of this, is anything that's not in the equation, you need to assume is constant. So let's say that on the ACP, they give you this equation right here, the one that you're looking at, and they ask you, what are the constants in Boyle's law? What would the constants be? I'm gonna mute. So let's go ahead and move on. All right, now we're going to talk a little bit about volume. So here we have area. Area is a two-dimensional representation of a 2D space. So this one is going to be 25, and we'll call it centimeters squared. And then over here we got volume. Volume is a 2D representation of a three-dimensional space. And this one is going to be 125 cm cubed. So in chemistry, we're only going to use cubes. We're never going to use these squares. That's the only reason that I included this. I wanted to show you the difference between a square and a cube. So volume must be input as liters. We always want to put our volume in as liters. And the three units that you're going to see most commonly for volume are going to be centimeters cubed, milliliters cubed, and liters. So these three units, I would write them down. I would write volume, and then directly underneath, centimeters cubed, milliliters cubed, and then liters. So anytime you see any one of these units, you need to know that this is volume. Now I want to show you how to convert from one to the other because you need to do that. So 1 liter is equal to 1,000 centimeters cubed. And it's really cool because it's also equal to 1,000 milliliters cubed. So 1 liter is equal to 1,000 centimeters cubed. It's also equal to 1,000 milliliters cubed. So if I tell you that you have 300 milliliters cubed, how many liters do you have? What is it? 0.3 liters. So all you do is you place your decimal, you move it over 3 spaces every single time. That sound easy enough? All right, let's go ahead and move on. So I like to entertain you guys with a joke every once in a while. What y'all think? All right, let's move on. All right, so next up, we're going to define pressure. I don't want you to write anything on this page down. This is kindergarten stuff. Don't worry about this. So what is pressure? Pressure is going to be force divided by area. So here we have 3 shoes. Don't worry about this question. We have 3 shoes. We got these high heels, these tennis shoes, and these Eskimo shoes. And I'm going to give each one of these a number. So I'm going to call this 1 centimeter cubed. I'm going to call this 10 centimeters cubed. And then I'm going to call this one 100 centimeters cubed. Now let's say that you weigh 100 pounds. If you weigh 100 pounds and you are about to stand on a frozen lake. So here's the frozen lake. It's frozen over. You're trying to stand on it. Which shoe is most likely going to break right through? It's going to be the high heel. So 100 pounds of force divided by 1 centimeter. You're going to have 100 pounds of pressure on this shoe, assuming you're standing on 1 foot. There's going to be 100 pounds of pressure on this one heel. Whereas on this shoe, what's it going to be? So this one would be 100 pounds of pressure. What would this one be? The 10 centimeter cubed. It would be 10 pounds of pressure. That's assuming you're on 1 foot. What about this 100 centimeters? It's going to be 1 pound of pressure, but it's going to be very evenly distributed throughout these shoes. There's so much surface area that that's just how it's going to be. So that's what pressure is. Pressure is very dependent on the area, and that's why I wanted to show y'all this. Pressure depends on what? Pressure depends on 3 things. It depends on the number of molecules. So the more air you pump into a basketball, the higher its pressure is going to be. So pressure depends on number of molecules or number of moles, however you want to put it. Pressure also depends on the volume of the container. So let's say we have 2 basketballs. We got this Spalding one, and then we got this little Dave & Buster's one. If we put 50 psi in each one, if we put 50 in this one, and we put 50 in this one, which one is going to have the higher pressure, the bigger ball or the smaller ball? The smaller one is going to have the higher pressure. So pressure depends on the volume of the container. The smaller the container, the higher the pressure. And then the last one is going to be average kinetic energy. So if we have two basketballs that were both at 50 psi, and then we put one in the freezer overnight, the one that we pull out of the freezer, will it have higher pressure or lower pressure? It's going to be lower pressure. And if you want to do this experiment, just take an empty water bottle, seal it, and then stick it in your freezer. See what it looks like the next morning. It'll shrivel up, yes. All right, so one last thing about pressure that I want to go over. So let me show y'all on this model real quick. So I'm going to clear this, and I'm going to pump in some air, and then I'm going to hit pause. What I want y'all to see is there's no pressure here yet. Why is that? What do we need for pressure to for us to see pressure? We need the particles to collide with the walls. If the particles don't collide with the walls, there's no pressure present. So as soon as they hit the wall, you see now we have pressure. So I'm going to reset that just to show you again. So pressure does not exist until the molecules bounce off the walls of the container. Why is that important? If you take if we take a basketball, so here's a basketball, and it's got 50 psi, or 5 psi, whatever, and then we put it inside of a sealed box. Is the box going to have the same pressure as the ball? No, it's not. Because the molecules are not bouncing off the walls of the box. They're bouncing here inside the walls of the basketball. And those collisions, are they elastic or inelastic? They're elastic, which means the particles are not applying any. They're not transferring any energy to the ball itself, which is not being transferred into the box. So the box does not have pressure. Only molecules hitting the walls of the box will produce pressure. And that's it. So collisions between gas particles and the walls of the container exert a force on the wall. That force is called gas pressure. And that's it. That's all I got for pressure. Now let's move on to units of pressure. So over here we got 5 units of pressure. There's one more that I didn't mention. There's probably a million more. But bar is another one that's not mentioned. Anyone know where bar is used? So scuba diving. So people who scuba dive, they measure their pressure in bars. So what is 1 ATM? So if you go to any beach on Earth, just go to the beach. At the beach, the pressure is going to be 1 ATM. That's what we determined the pressure is at sea level anywhere on Earth. So anywhere on Earth at the beach, you're going to see a pressure of 1 ATM. Now that 1 ATM is equivalent to 101 kPa, kilopascal. That 1 ATM is also equivalent to 760 torr. What is 760 torr? It's just a rename for millimeters of mercury that never worked out. So now you still see millimeters of mercury and you also see torr. So millimeters of mercury and torr are the same thing. So these two are the exact same, but you're very likely to see both of them on homework, classwork, and exams. You're going to see both of them. And the last one, because we live in America, we got PSI, pounds of pressure. So these are all the units of pressure, and the way my students usually remember them is if it looks weird, then it's probably a unit of pressure. So ATM, torr, these are both new things, kPa, mmHg, PSI. These are all new things that you don't associate with anything else. So go ahead right now, associate these with pressure. If it looks weird, it's pressure. All right, now next thing I want to talk about is STP. Anybody know what STP stands for? Standard temperature and pressure. I think we mentioned it last week. So all I want you to know about standard temperature and pressure is standard temperature. I don't want you to ever think it's 0 degrees C. I want you to know that it's 273 K. So 0 degrees C and 273 K are the same thing, but we're never going to use Celsius in chemistry. We're always going to use Kelvin, so it doesn't matter that it's 0 degrees C. Just know that it's 273 K. Now, anytime you're not given a unit for pressure, I want you to use ATM. So 101 kPa, you don't need to know that. All I want you to know is for standard temperature and pressure, it's going to be 1 ATM, and then it's going to be 273 Kelvin. So what is STP? It's 1 ATM for pressure and 273 Kelvin for temperature. Y'all excited about playing the game?
This a game?
Yes. It's a gas laws game where we answer gas laws questions.
Is it on like look it or something?
It's not an assignment. It's a game.
Is it on look it or something?
It's something like that.
No. You should do it in
All right, let's go ahead and move on. All right, so we're not going to talk about temperature today. We're going to talk about temperature next time because we're not doing any of the laws that include temperature today. Today, we're only working on pressure and volume. So we'll come back to this slide. We'll come back to this temperature practice. All right, so these are two things that I do want you to write down. So this is regarding the relationship between temperature and pressure. So at lower temperatures, that means when it gets colder, at lower temperatures, gas molecules move slower and they exert less pressure. I'm pretty sure most of you already know this. If you know this, there's no reason to write it down. If you don't know it, I would definitely write it down. So at low temperatures, gas molecules move slower and they exert less pressure. At higher temperatures, that means when it's hot, gas molecules move faster and they exert a greater pressure. Anybody know what's being poured on top of this pour balloon?
No, it's just the cold one.
It is cold stuff.
The very cold one.
It's liquid nitrogen.
Yeah, liquid nitrogen.
So liquid nitrogen is it's cooling the gas inside of the balloon real quickly, causing it to shrivel up. All right, anyone need more time on this? I just realized I've been muted this whole time. All right, so as you can see, as we decrease the pressure, you're seeing that there's a slight increase in volume. You're going to notice the biggest difference in volume once we reach about the 10 meter mark, because that's when it's just going to double. So here we are, 20 meters, 15 meters, and I'm going to slow it down here. And there we are. We're back to original volume. So I just show you all this so that you have an understanding of why pressure and volume cause each other to change. I don't want you to just believe me. I don't want you to just do these math problems, just plug in the numbers and I want you to have an understanding. So looking at this chart, the whole point of this chart is to show you guys that as one of them goes up, what happens to the other one? So over here, our volume is increasing as we go down. So as we go down, our volume is increasing. We go from 10 to 20 to 30 to 40. So as volume increases, what happens to our pressure? It decreases. So as this increases, this one decreases. And that's the relationship that you guys are gonna notice. So let's go ahead and move to the next slide. So this is all the notes that we're gonna be taking today. We're just about done. So this right here is the formula that you're all gonna need to write down. So P1 times V1 is equal to P2 times V2. I would like for you to also draw this chart. If you guys remember correctly, this is the only this is the only chart that looks like this. All the other charts, nope. All the other charts for the gas laws we're going to talk about look like this. This is the one that's different. What does that mean about it? Why is it different? Is it directly related or indirectly related? It's indirectly related. It's an inverse relationship. And another thing I want you to notice, and we talked about this in the beginning of class, what are the constants when it comes to Boyle's law? What are the constants? Moles and temperature. Good. So anything that you don't see in the equation is a constant. So I'm going to give you guys a few more seconds to write this, and then we're going to move on to our practice. How do you say, all right, y'all, let's go ahead and move on. So these are the other laws that we're going to talk about. We're not there yet. So here we are. We're going to do these practice problems together. So the first one I'm going to do myself, and then the last three, everyone here is going to do on their own. So please pay attention to how I solve this. I want you to solve yours exactly the same way. So first thing I'm going to do is right at the top, I'm going to put in our equation. So we got P1 times V1 equals P2 times V2. And then over here, you don't need to do this part. This is the part that I definitely want from you, though. So down here, we're going to put P1, V1, P2, V2. And then we're going to plug in our values. So let's read this. It says, what pressure is required to compress 196 liters of air at 1 atmosphere? So I'm going to pause right here. So 196 liters of air at 1 atmosphere. Is this initial or final? This is initial. So 196 liters, what's that? That's going to be V1. So 196 liters. And then what's 1 atmosphere? That's P1. So that's going to be 1 ATM. Now down here it says into a cylinder whose volume is 26 liters. So what's that? That's going to be our V2. So 26 liters. Now this is our unknown. So I want to see this section right here on everybody's paper. Now that we have our information, we just need to plug it into our equation. So we got 1 ATM times 196, and that's going to be equal to 26 times P2. It's very important that you include your variable in the equation. If you don't do that, it's going to provide for problems later. So please make sure to do that as we do these. So first thing we're going to do is we're going to multiply the two numbers on this side. So 196 times 1 gives us 196. And then lastly, we just want to isolate the variable. And we're going to be doing the same thing in all of the gas law problems. So we always want to get the variable by itself. So to get P2 by itself, what do we have to do?
Divide by 26.
We have to divide. And the reason we're dividing and not subtracting is because these are being multiplied. And to get rid of something being multiplied, you just divide it. So divide by 26. Now this goes away. So P2 is equal to 196 divided by 26. Could someone plug that into a calculator?
7.5.
So P2 is equal to 7.5. And what's our unit? It's going to be ATM. So same unit you plug in, that's the unit you pull out. Any questions? All right, let's go ahead and move on to the next one. I'm going to give you guys 3 minutes. Like shh. Man, and I just realized I've been muted this whole time. All right, shh. All right, so there are 65 liters of helium in a balloon at 35 degrees Kelvin. If the temperature of the balloon was increased to 40 degrees Kelvin, what will the new volume of the balloon be? So looking at this, which law do you think we're going to use to solve it? So here they give us liters. So what's this? That's volume, right? So this is V1. And then what's Kelvin? So this is going to be T1. Over here they give us T2. And they're asking us for V2. So we're going to have to use this equation right here. So this equation is going to be V1 over T1 equals V2 over T2. And then we just plug stuff in where it goes. So this is going to be 65 over 35 is equal to 40. And then up here is our V2, which is what we're solving for. And then to solve this problem, we just cross multiply. You call this cross multiplication, right? I don't know. So 65 times 40, that gives us 2,600. And then we bring down the equal sign. And then 35 times V2. And then we solve it just like we solved the one before it. So we isolate the variable by dividing both sides by 35. Then this goes away. And then 2,600 divided by 35 equals 74. And then that's our answer. So V2 equals 74. And then the unit for that is going to be liters. And that's it. Have a good rest of your day. Get the assignment done for y'all. The assignment's going to be posted online.